Morning. Welcome to the ASM Journal Computing Information Science Engineering JCISE Spotlight Talk webinar. Today, it's my pleasure to introduce our speaker, Dr. John Markopoulos, who's a Director of Computational Multiphysics System Lab in Naval Research Laboratory. John has been the expert, a well-known expert in the field of computational mechanics, and particularly in the past 40 years, John has contributed tremendously in the multiphysics simulation. And today, it's our opportunity to learn the latest work on the Elasto-Plasticity damage and multiphysics effects, on this joining. And so this is our latest paper published at JCISE. John, please take over.
Yang, thank you so much for the very kind introduction. I like to take the opportunity to say that this is a talk that coincides with the 100-year anniversary of the foundation of Naval Research Laboratory. And I'm particularly honored to represent the co-investigators and co-authors of this paper, Drs. Apeter, Eliopoulos, and Steuben. And the topic, as Jan mentioned, is the elastoplasticity damage and multiphysics effects on the behavior of adhesive step-lap joints. So first, what is the problem? What is the problem with adhesive step-lap joints? And the importance of this comes from where they are actually being used. So here you see an F-18 fighter, A to D series, which essentially is one of the main naval fighters, and we need to connect the composite material skins to the superstructure. And if you look at this area and you cut it through, you'll see that actually that skin, the composite skin that's shown here with a black domain, is actually adhered to the titanium splice, which actually is stepped. It has 9 or 11 steps. And this is a technique usually, we use in other industries as well, like wind turbine industry, where we have two materials that we need to connect together, and we have to use an adhesive to play that role. Now, these joints, however, not only experience mechanical loads, but they also see heat transport and hygroscopic moisture mass transport, and obviously damage evolution adhesive layers. Now, the problem is that there are many failures on these adhesive step-lap joints, and they have severe implications on the operational readiness of these platforms, like the F-18. And it turns out, we've been asked to investigate what's going on, and we found, to our surprise, that the design and qualification practices consider only elastoplastic structural mechanics and do not include any multiphysics stimuli like temperature and moisture coupling. And the question now is, could the fact that we ignore those things have an effect? Should we actually consider them? And can we actually do the qualification based only on structural mechanics? So for that reason, and to answer some of these questions, we actually decided to create a multiphysics computational framework for assessing the state and performance of adhesive step-lap joints. And this is what I will be presenting to you. So when it comes into the physics involved, if we really want to account for the hygrothermal structural interactions, we have to consider the conservation principles that are associated with the physics participating in this case. So first, we're going to have to allow the conservation of mass to be applied for a field, which in this case is going to be C is going to be the field that expresses the relative humidity inside the medium. And as you can see, its evolution doesn't only depend on that, but also depends on the temperature due to the coupling that it has. Similarly, in the energy conservation form, which essentially is the heat equation in the local form, you see that in addition to temperature, we have here moisture, but also we have mechanical effects. We have the strains that play a role. And last but not least, from the conservation of momentum that we have to solve for structural mechanics, in addition to the traditional form you see here on the left, you see that there are body forces terms that are coming out from the temperature and moisture gradient. So really, we have to solve this system of partial differential equations for all the appropriate cases that are of interest to us. So when it comes to the plasticity formalism, we essentially, this is nothing new. We're just making sure that we use a flow rule, we use the three Kuhn-Tucker conditions, and a von Mises failure criterion, because we actually assume that the adhesive that we are looking for is isotropic and homogeneous. Then, for the damage formalism, we essentially take consider that the actual final stress is a stress that is degraded. This is the undamaged stress tensor, and this is the damaged stress tensor. And the relationship is through a multiplier that has this damage parameter, which obviously when is zero, there is no damage, then the two stresses are the same. But when it gets close to one, then it gets degraded, and it's a lower stress because obviously the material has been damaged. Then we need to have a loading a function implementation equivalent to the Kuhn-Tucker conditions for basically ensuring that the material is not healing itself when you unload. We can actually use a Rankine stress damage model for how the equivalent strain evolves as a function of the elastic strain and the loading. Here you see another potential, one of the many potential expressions that we can use for this D that you see here, how it degrades. This is an exponential law that depends on the fracture strain, which in itself depends on the fracture toughness and the strength of the material. We actually used additional forms of the softening function, as you will see a little bit later. So the computational framework developed, really first we applied it for a realistic configuration, but first in 2D. So you see a 2D that has two adherents, one on the top and one on the bottom, with these 4 steps. The adherents we consider, as you see later actually, are titanium, and the adhesive are really this red thick line, which essentially are 6 millimeter long and about 0.1 millimeter thick. And we went to all the potential configurations of what mechanics are here, the plasticity in terms of at least 2 forms, a perfectly plastic isotropic hardening, a multilinear one, the Ramber-Osgood non-linear one, a progressive damage formalism that had a scalar damage parameter, as I mentioned before, and of course the hygrothermal structural model that integrates heat and mass diffusion inside the medium. The numerical finite element modeling was implemented in COMSOL Multiphysics, and to the right here you see an example of a mesh that shows the densification at this adhesive layer. And depending on the physics we really use, that is a model that is relatively manageable easily on a small system, and it varies depending on the physics and depending on the nonlinearity models that we use, anywhere between 0.5 to 1 million degrees of freedom. Now about the material properties, and here is really one of the big problems. The material that typically used for these cases, and the one we chose for the analysis, is actually this Cytec FM300K, which is a well-established material and has been used in multiple applications. But the problem is that the manufacturer provides very rudimentary material properties for room conditions, and not necessarily for all the conditions that the material can actually see. So the properties can be really very nonlinear, can have very nonlinear dependence on temperature, as you can see here. And I highlighted here with this gray area the area of temperature that we are interested, which basically maps to the operational envelope of how what a fighter sees when it goes from the ground up and it cools down. So we're looking for cold behavior of this adhesive as opposed to hot. And while we have experimental data for hot for high temperature cases, the data for colder areas of operation are not really well known. So the last point we get is, as you can see, for Young's modulus here, and now we really are faced on how we're going to deal, what we're going to use in the model for this. So we have two options. One is to extrapolate to the left, keeping a common tangent at the last point. Another one, which is really making it a little bit more conservative, is to take just a horizontal line. And a third one, of course, is to just take something in between. Clearly, we need data here, but for the sake of the analysis, we implemented the one we've seen here in the middle. Again, same thing for the nonlinearity. You see the distribution of the strength and the ultimate strength and the yield strength distribution. And on the right, you see the fracture energy per unit area distribution for mode 1 and mode 2 fracture. The adherents, as I mentioned, were Ti64, and Ti64 also have a variable, but in this case, more linear dependence on temperature. For example, you see Young's modulus with the blue line here, and you can see Poisson's ratio with the red line here, and the density and thermal expansion coefficient on the right side also seem to be linearly dependent on the temperature that we are actually solving for in the energy conservation equation. So what are the boundary conditions for this problem? We really try to find some boundary conditions that locally represent what the joint is going to see as a result of the flight conditions. So in this case, we fixed the right end and we applied a load here on the left side that is either horizontal or vertical or combined because of the bending that the skin layer sees on the top and the bottom of the wing. That is a symmetric model, so this is a symmetry plane. And then we applied the environmental boundary conditions on the outside, both heat flux and humidity conditions that go up to this gap that you see here with my pointer. The flux we use really also itself is a convection-based one, and the temperature depends obviously on the altitude, and the convection coefficient also depends on the altitude. And since the service ceiling of the F-18 is about 15 kilometers, we basically took a linear ascending and a linear descending trajectory, and of course that corresponds to about 250 meters per second, typical for this vehicle. And we use this time dependence for the temperature applied in this formula here for the flux, and the red is the convection coefficient. Now, for the humidity on the conservation boundary conditions on this side, we assume that the plane at some stage goes through a very wet cloud, and for a period of time, it stays jumps from 40% to 140%, and the applied displacement also, we've made it to be linearly dependent, so we can actually compute a performance parameter by exercising the framework that we can compare the effect of the various physics and the various assumptions to each other. So we have on the left here, you see a table that shows you all the potential problems that we can actually solve with this framework. We have a problem of ascending and descending that affect the boundary conditions. We have an applied displacement that can be horizontal or vertical or both. We can have the physics that can be structural, thermostructural, or hygrothermal-structural. We have the material nonlinearities coming from plasticity. We have the material nonlinearities coming from the softening of the adhesive due to damage. We have also the fact that we need objectivity on the damage formalism. We require some regularization method, and there are at least two techniques, the crack band technique and the implicit gradient technique, that we actually can exercise. And then, because we do not have some of them very important properties at the end, we perform some parametric studies to see how those the variation of those things that we do not have, but we can postulate what effect they have on the results. So I'm not going to, out of all these combinations, we actually and we presented in the paper what you see here on the right. And I'm not going to stay on this table, but I'm just going to go directly to the results. So first, let's see the regularization method effect. The crack band versus the implicit gradient regularization technique for all the structural mechanics physics only, where we have the elastoplasticity, the pure elastoplasticity on the blue line, and the Ramber Osgood on the orange line. And then all the in-between ones are the various types of damage. As you can see, these regularization techniques do have an effect on the damage lines, but it's not really crazy. You can actually, it seems that you can actually select one or the other for this case and still be able to design with some safety factor and account for this variation, the small variation that you see between the two methods. Then we go to the mechanics only loading by axiality effect. So these are all the mechanics models that actually the framework allows us to exercise. And here, the left one is horizontal displacement, and the right one is for vertical displacement. And remember, this vertical axis is the reaction force that is being experienced on the side of the joint that we keep fixed, and it's a global performance parameter versus the horizontal axis, which is the applied displacement as a function of time, which goes up to 0.12, as you can see here. So the effect indicates that indeed there are obviously, as expected, some variability based on the fact that the two loads are different and they activate the resistance of the joint differently. That's not really surprising. The next thing is the difference between ascending and descending, or when we start using the various multiphysics effects. First, we did it without using the multiphysics, so this is just the mechanics, which essentially means that the ascending and descending variations come from the fact that the boundary conditions on the temperature and the humidity, on the temperature only, because here we don't have humidity, are the ones that are applicable. So again, you see that here we start getting significantly different results when it comes to the softening and the damage between the two cases. So load history of a vehicle has an effect on what really the joint sees, which already opens the door to assume that we cannot really to infer that we can no longer assume that the behavior of the joints are independent of the load history. So now we wanted to start looking at the biaxiality effect in terms of the additional physics. So the purple line shows hygrothermal elasticity with damage. The blue dotted line shows exponential damage mechanical, and the red line shows thermoelasticity with damage, in addition to the two plasticities, Ramberg-Osgood, regular multilinear plasticity. So as you can see, again, the horizontal displacement and the horizontal and vertical displacement at 45 seconds after the the history that you saw on the boundary conditions actually presents this evolution. Again, very drastic difference here in terms of how damage affects globally the force displacement curves. Next, I would like to show you again the loading history effect, the ascent versus descent for the various considerations of the multiphysics. And again, here we do have, as you can see, especially for the hygrothermoelastic case, which is the purple line, we do get significant variation between ascending and descending. Now, I'd like to really point out that since the strength and the fracture energy are not really experimentally observed, we decided to really do a parametric study, and we kept the strength the same and vary the fracture energy. And you can see the lines here for each one of these cases. And then we reversed it, and we kept the fracture energy constant for one value that we found in the literature, and then we vary the strength case, parametrically. And this is really the first important result that is being highlighted by this ellipse. We see that for certain values of the strength, we can get a deviation from linearity much earlier than plasticity is yielding with the damage model, which says that if indeed there is a dependence of the strength in some parameter that relates to the performance of the plane, then designing for elastoplasticity is no longer the conservative choice. There is a much more dangerous situation for the yellow and the green lines that we need to account. So how does this damage look like? So let's look at this layer, which is really the most critical one. That's the one that is the higher concentration of stresses and damage and strain and density accordingly. So here you see the comparison between having just elasticity with an exponential damage law, only structural mechanics. On the right, you have thermoelasticity with an exponential damage law for the ascending and descending. And you can see really for the crack model how really the thermoelasticity is becoming really much more aggressive than just the elasticity with damage. Gets much more saturated in terms of criticality on the right side than there is on the left. Now, in terms of the biaxiality effect, what you see here is on the left is the horizontal force, and on the right is the vertical one. And we use, obviously, like in the previous case, the crack band model, such that we can get these localizations of concentration of damage. Remember, damage is a parameter that goes from 0 to 1. So red is 1 and blue is 0. And you can see for the various models, this is the exponential damage, this is the thermoelasticity with exponential damage, and this is the hygrothermoelasticity with exponential damage at the 45 seconds, as I said before. And you can see the difference left to right in terms of the loading thing. There are differences. They're not really very drastic, but there are consequences of the fact that the load redistribution is different because of the boundary conditions being different on the side of mechanics, while on the side of thermal and hygrothermal effects, they are the same. But yet, the condition that contains all the physics is really the most critical one, as you can see on the bottom two graphs for both load modes. So how about stored energy density, which is really joules per square meter in this case, and it's actually the quantity that many failure criterion can be formed and discussed about. Again, we see the comparison that you showed 2 slides ago between the structural mechanics with an exponential damage law and the structural mechanics with thermoelasticity and exponential damage law. Again, when you have the thermal presence, things becoming much more critical. And I kind of indicate that maybe it's time to start considering designing those things by not ignoring those effects. Here is really a long list of the localization of the strain energy density for all the physics cases that we've got, including the Ramberg-Osgood plasticity, which clearly doesn't have damage, that's why it's uniform. The multilinear damage, that it does show localization, the polynomial damage that shows also localization, the linear damage, also the exponential damage, the plasticity, which obviously is like the Ramberg-Osgood because it doesn't contain damage, the thermoelasticity with exponential damage, and the hygrothermal-elasticity with exponential damage, again, being the most critical of all in terms how much of the material gets into close to 1 in terms of being softened completely. So what do we conclude out of this? We conclude that this framework shows us, many cases the responses generated, and that the plastic material responses, it's a conservative case, and we can perhaps use it for some cases, but there are cases where the nonlinearity begins before yielding, and if damage is accounted for, the elastoplastic behavior may not be the most critical. And therefore, we really have to start thinking whether indeed design and qualifications should account for this. It is critical also to properly characterize the damage model parameters, which here we had to select based on prior experience, which is not necessarily always applicable for a particular case. And then when accounting for heat transfer and mass transfer effect, the characteristics of the flight path impact, the global response and the local damage energy density within the adhesive can be very different than the one we saw from structural mechanics alone. And again, I've said this many times, but I think this is the most important thing. We have this analysis shows that there is really a reason to start considering the fact that it may be necessary to start considering design and qualification of ASLJs by accounting for damage and environmental conditions instead of just elastoplasticity. So in terms of the path forward, we obviously need to validate the framework with appropriate experimental campaign. This is the highest priority. We certainly want to develop a 3D digital twin family for realistic ASLJs, for heterogeneous adherents. You have one side composite and the other side titanium, as opposed to just titanium, to address the sustainability concerns for relevant platforms that use those joints. We also want to account for the stochasticity introduced by manufacturing and operation conditions as they evolve while the platform continues to operate, in this case, fly. We also want to perform inverse characterization of unknown properties under all this variability of ranges for the conditions that these materials behave. And this is really a critical part that also determines the quality of the predictions of the models used in this framework. And we want to extend ASLJ durability considerations, for lifing them, in terms of basically accounting the multiphysics and loading by axiality that is being induced by the realistic flying conditions to enable environmentally informed design and qualification. And with that, I'd like to thank you and take any questions.